Good evening to all. Thanks for joining. Today we are going to discuss a few questions from the content from week 8. And this is the interactive session for the course Foundation Engineering taken by Professor Kousik Deb. I'm one of the TAs, Kashyap Vasudevan. And okay, so let's begin today's session. So as usual, let us start with the recap about the last week, week 8. So in week 8, our instructor discussed a lot of things in the sense one of them being the dynamic formula for file. Uh, in this one, the basic idea is uh, we are trying to judge what is a pile capacity by observing by comparing the energy applied and the work done. So by checking how much energy we are applying on the pile while driving it. So obviously this is specific for driven piles. So we can estimate roughly the energy applied on the pile, and we also know what is the work done, that is the displacement of the pile after the hammering is done. So by judging these two quantities, the work applied as well the work done as well as the energy applied, we can roughly estimate the capacity of the pile. So there are basically two formulas used for that, two popular ones. One is the engineering new required formula. So that is the first one, and that can be written as QA is equal to WH by F into S plus C. Here, um, this is for engineering new record formula. So this formula, in this formula, it's quite clear that since this is the weight of the hammer, and this is the height of drop of the hammer, and this is a factor of safety. Uh, it's generally taken as 6, and this S plus S and C are nothing but it collectively shows the settlement, and so the idea is Q, it is the force into displacement is equal to the work done. So so this is the displacement part in that. So SS represents set per blow, that is a settlement per blow, and C actually indicates the energy loss. So for each type of hammer, there are different values for C, like 2.5 for drop hammer, 0.25 for single acting beam steam hammer, like that. So that's the basic idea. Similarly, one more equation is there, modified Haley's equation. In that equation, the efficiency of hammer blow and efficiency of hammer. So efficiency of blow, that is energy transfer, and the efficiency of hammer is also taken into account. So that formula looks like the ultimate capacity is directly given as weight of the hammer into drop of the hammer height, the height of drop, then efficiency of the hammer and efficiency of the blow divided by S plus C by 2. Again, it's nothing but the same. Here factor of safety is not there because directly we are getting the we are getting the ultimate capacity of the pile. So that is the idea. So here the efficiency terms are included of hammer as well as pile. Problems on this was solved in the last session by Mr. Shivshakar Nandi. So this is the first portion. So in the subsequently after this topics were discussed, our sir he discussed more about correlations to arrive at our pile capacity using static concentration test as well as standard concentration test. So in static count penetration test as well as this is actually clearly mentioned in the IS code. So both of this can be found out in IS 2911 1 comma 1 first part first section, which is dedicated for driven piles. And in this annex, if you go to annex B, I'll really recommend to go to annex B, because all the things that we are discussing in this subject, many things are mentioned here. So uh, even when you are practicing in field, it will be very useful. So it's better to get thorough with this particular portion of this code. And in annex B, part 3, in part 3 deals with SCPT data, and B4 deals with our standard penetration data. So using this data, there are correlations that we can arrive at our what to say ultimate capacity of the pipe. Now, so when I say SCPT data, we have static count resistance. Using that value, whatever we get in the field, we can directly arrive at our capacity. And here, SCPT data, when I say, that is nothing but the SPT number, the corrected number. And using that, there are different correlations to arrive at our capacity. Okay. So but things that we to understand is that in a certain way this is superior, because we are directly getting the resistance value from the field. So the data that we are using here is directly from the field. So the in a certain way we can say that the values that we are getting from these methods are reliable, because here in the dynamic equation, we have formula, we have weight of the hammer and all, which is directly which is part of the test done in the field. So, and in the correlations we have obviously SCPT and concentration data. So okay, so here it is standard penetration, sorry. So now but earlier we used to arrive at our pile capacity from our data that we have obtained from the laboratory. So in a way, this method should also be known by the geotechnical engineer, because in different scenarios this will be more superior. Okay. After that, we went through this group action of piles. So within pile is generally provided in groups, rather than giving as a single pile. We give it in groups. So in group, when we are giving in group, we need to understand the group action of piles. When I say group action of piles, this is what happens is when the piles are closely packed together, we need to understand the mechanism behind it. So if it is too much closely packed, the influence zone will overlap. So especially when it comes to very hard soil, then soil and all, it won't be of any advantage, because the overlap of this influence zone can cause failure earlier. So to avoid that, we have to give a certain spacing. At the same time, when the soil is loose, this group action can be very advantageous for the foundation, because it can increase the capacity. So because the loose sand after driving, it gets packed. So in the overlap region, it is very dense, and that increases our efficiency. So hence comes the term pile group efficiency. So we have two terms, that is the capacity of a single pile, and we have capacity of group pile. So what is happening is, when we have loose sand, this group capacity is higher than number of piles into the single pile capacity. So that is the idea, but this is actually only found in loose sand. So when we are doing our design, we will assume it the efficiency as one. So hence comes the term efficiency, pile group efficiency. So we have the group capacity divided by number of piles into one single piles capacity. So this is the efficiency of the, so if you multiply by 100, we will get the efficiency in percentage. So uh, this is the idea behind finding the efficiency of the pipe. So okay, after that we went to the so after that we went to the settlement of pile. In settlement of pile, it's very much similar to pile group. It's very much similar to our shallow foundation settlements. But what we have to understand is there are three different cases. For example, depending on the stratigraphy of the soil and whether the pile is friction pile or end bearing pile, we'll come to that. We are solving a problem related to that. And after that, sir also discussed about a particular problem, design problem in full length, like from the capacity of the pile settlement and to decide what are the dimensions. And after that, so I would really suggest you go through that. So that question encompasses many concepts. And after that, he went on discussing about our negative skin friction. Negative skin friction is found in certain cases when our soil is settling faster than the pile. So what happens is when soil is settling faster than the pile, it will drag the pile down. So which is counteracting our resistance. So it adds on to the load. So our capacity reduces. So that has to be taken care whenever we are dealing with such situations. So otherwise we'll end up overestimating the capacity, which is disastrous. So considering negative skin friction is also very important. We'll solve a problem. We'll discuss more on that. And the week ended with the discussion of precast piles. So he just slightly discussed about the transportation of precast pile. So what the issue is like. So when we are transporting piles, the concern is that when we are precasting it in one place and we are transporting the precast pile to the field, and in the field we will drive it. So driving, so there are different stresses that is acting during these processes. Uh, uh, there are stresses when after when we are taking the pile from the place A to B, and there is also stresses that is acting on the pile when we are driving the pile to the ground. So so we have to consider all these things. So that's why there is two types of lifting, that is one point lifting as well as 2 point lifting. In both the cases, the stresses acting on the precast pile is different because 1 point lifting will cause more moment and than 2 point lifting. So that was slightly discussed. And because this thing is important because these stresses will govern the how much reinforcement has to be given to the pile, because flexural stresses we are not expecting much on piles during its action as a foundation. However, when we are transporting the precast pile from point A to B, and when we are lifting it in 1 point lifting or 2 point lifting, flexural stresses are acting. It will act as a beam because we are giving support laterally, and the self weight will act as a uniformly distributed load. So that will cause flexural stresses. To resist those stresses, we have to give reinforcements accordingly. That is the idea for behind this 1 point lifting and 2 point lifting. So that will be more discussed later, as well as laterally loaded pile will also be discussed later. So uh, so that's how our week ended. So let's jump on to our questions first. So we have a few simple questions this time. So we'll solve it fast. Uh, okay. The question one deals with uh, friction. Okay, we have 9 friction piles and square pattern. It rests on soft clay. Okay. Now, the group was constructed such that the performance of the group efficiency is equal to unity. If the center to center spacing is 1.2 meter and unconfined compressive strength is 80 kPa, estimate the diameter. So here we are trying to estimate the diameter of the pile having given everything. So okay, we are also told to neglect the tip resistance, and alpha value is also given. Okay, so let us try. So here before we begin, let us see what are the things we need to understand. One thing is like it's as same as we had done before, but the only question is which is higher, the group capacity is higher, or the individual capacity into the number of piles is higher. So whichever is higher, whichever is lower, we'll have to consider that. So, okay, but generally group efficiency will be greater than one in sandy soils. But here efficiency is already given, so both should be equal. That is a very good clue. So we can equate the group capacity as well as single capacity into the number of piles. So let us do that. So here to begin with group. So let us say what we are given. We are given that our group efficiency is equal to our group capacity divided by n into number of piles, n is number of piles, into a single pile. This must be equal to 1. That's what we're given. But we also know that the group capacity can be written as our just as before. We could say CNC into AB plus what will be, this is a bearing, the bearing resistance, and uh, the cohesion part, so the skin resistance part. So to write the skin resistance part, we need in this case alpha Cu and As, right? So As is the shearing part. But here if you remember, we had discussed last time, alpha will be uh, 1 in the case of group capacity, because here the when we have when we are taking this block failure from in the plan, it will look like this. The failure surface will look like this, and the failure surface, the interface of the failure surface is between clay and clay, so our adhesion will become 1. That is one thing in the case of group. The question is also mentioned that neglect the tip resistance, so this is not our interest. And our single pile, if you are taking the single pile, the same thing holds good. Cu NCAB, this time this is of the pile, here it is for the block. uh, uh, so alpha Cu A. So basically the equation remains the same, but here alpha will not be equal to 1 because we are taking for a single pile and we will be multiplying it later into the number of piles. So we are taking the single pile. So but here also we can neglect 0. So why are we neglecting it as 0? Because it is basically friction pile, so our frictional resistance is more important. So it's safe to neglect the tip resistance, because anyway it will be in the conservative side. Okay, so let us start and see what happens. So we have QUG is equal to since the first part is not there, so I can write uh, CUAS, right? And the QU is will be equal to alpha CUAS. Alpha CUAS. Remember this AS is for group. Okay, I'll write G suffix just to tell it as group. So here I'm writing it as G just to show that it is for the block, the group, pile group. Okay. Here, what is our CU? CU, they have given QU, that is a UCS value, that is an unconfined compressive strength test value, as QU, that is 80 kPa. So our CU will be 40 kPa, the half of the UCS. So let me just reduce this a little. Now, having said that, we know the efficiency is 1, so our 1 is equal to QUG by N into QU. So our QUG is equal to cohesion Cu ASG by uh, N is 9, so N into alpha Cu AS. So this AS is just for one pile. uh, okay, now I can cut cancel CU and I'll get N alpha AS is equal to ASG, right? Okay, so I can stop it there. Now let us see the layout, how it looks like. So in the question it said that the center to center spacing is 1.2 meter. So I can say this distance is 1.2 meter. So my total this thing width of the pile group will be B is equal to 2 into 1.2. That is for sure. That is a 2 times spacing. Plus I have uh, half diameter here and half diameter here. So this will be d by 2 and d by 2. So that will be plus d, right? So both the sides d will be there. So I can write this as 2.4 plus d. So uh, okay. So diameter is the thing that we're trying to find out, right? So, okay. So d we will keep it as a variable and we'll substitute it here. Uh, and our number of piles is nothing but 9, right? 3 into 3. Okay, so let us see what happens. So 9 into alpha. This alpha is for our pile. So it is concrete with concrete soil interaction adhesion. So we have zero point 0.9 into AS. The skin resistance, the area subjected to the skin resistance, that is the shaft area, that is nothing but uh, pi d, right? Pi dl. So pi into d into l. L, do we know L? Actually we need not know L because L will be there in RHS also. And ASG for the block. So for the group, what will be the shaft resistance? That will be the perimeter of the pile group. So we know the width of the pile group. So perimeter of the pile group is 4 into B. That is B is nothing but 24 plus 2.4 plus D, and that's the perimeter into length of the pile group, that is L. And what else? CU. No, CU is not that. ASG. Okay, I think that's it, right? Length of the pipe. Okay, 2.4. Okay, that's it. This is shaft resistance. Shaft area subjected to the shaft resistance. Okay. So here I can cancel out our L and L, and what rests is we'll get a simple equation, something like 1.157 2.4 d is equal to d. So we can plus 2. Okay. We can simplify this and we will arrive at d is equal to 0.4476 mm. So this turns out to be uh, so we can say we can conclude the answer as like, since we are getting a number like this. Okay, this is not mm, this is in meter. So in mm we can write 447.6 mm. We can round it to, while constructing, we can round it to 450 mm. That is the answer we require. So we have one of the options, 450 mm. So that is the way to do it. Here the idea is, during design we'll take the efficiency as 1. It is mentioned in the question itself. And so we can equate, we got an equation, so we can equate, and length doesn't matter here, even cohesion doesn't matter, because it will get cancelled at both the sides. Okay, so having said that, let us go to the next one. Here what do we have? We have a pile of 0.4 diameter recently constructed with the fill. Okay, This is a recently constructed field. That is the reason it is having a very low density. The density is very low because it's recently filled. So angle of internal flexion is given. Depth of the fill is also given. Uh, Calculate the, okay, this is a printing mistake. Okay. Calculate the negative skin friction. Okay, we are supposed to find the negative skin friction. Uh, so here comes, due to this we know K and delta. Okay, so this is a cohesionless soil. Uh, since it is a very recent fill, we are expecting a settlement. So that will contribute to a negative skin friction load. So it's very straightforward question. Uh, so we have phi, we are given phi is equal to 30 degree, and this is the fill. Let us say this was the old ground level, this is a new ground level. So this is the fill, and okay, so let me erase this will give a better idea. So this was the old ground level. So we filled it with the soil with our very low density, that is 15 kilonewton per meter cube, and we drive a pile through it, and this is 3 meter thick. So what happens is, we have there is nothing much asked in this question, because we have to just calculate the negative friction load. That is nothing but the shaft resistance of this portion which is within this soil layer, which is going to settle. So what is happening here is, during the settlement of this soil, there is a downward force, which is actually additional to the our superstructures load. So actually whatever we are calculating for the superstructure, we have to add this, right? So that is the idea. And for resistance, we have this lower portion. So that is the catch here. Only the lower portion is providing the resistance, and if it is end bearing also, we have to show. So let us say this is the capacity, and capacity of the file, and our negative skin friction is, let us say it's as QNF. So that is the idea, but here we are just asked QNF, so we just need to find our the shaft resistance in that portion. That is nothing but our basic equation that we had discussed in before, well before. We have a K horizontal pressure into this is our friction, and tan delta is the friction, interfacial friction, and the area, that is a AS, that is a shaft area. So that will be nothing but we have K value as 1 sigma value. Okay, so we need to find sigma. So what sigma is, if you remember, it is the average effective overburden pressure in that layer. So here it is 0, and here it is gamma h. So we can take gamma h by 2 at the middle layer. That is the idea. So sigma average is equal to gamma, that is 15 into middle of the high, that is 1.5. That will be nothing but 22.5 kPa. And delta, we need to find delta, that is 2 by 3 into 30 degrees, that will be nothing but 20 degrees. So we have K value as 1, sigma value as 22.5 into tan 20 degree into AS. Okay, so shaft resistance is the shaft area, the area contributing for the skin resistance, that is pi dl, right? So yeah, the diameter of the pile is zero point 0.4 meter. Yeah. So pi into zero point 0.4 into length of that particular layer is 3 meter. So I have to correct 3. So this is as simple as that. We have to just do this calculation. That turns out to be 30.87 kilometer. It's a very small question, so we have an answer, I guess. Yeah, we have 31 kilonewton. That is the answer. But there are a little takeaways here. So here, uh, one important thing is like since we have these components, how will we find our factor of safety? So it is already discussed in the class. Factor of safety will be taken as we have the load. So resistance. So the resistance is QU. This QU comprises of both shaft resistance and the bearing resistance at the bottom. So that is this QU divided by our load. So our load is Q. This is our working load or the load that we are trying to apply on the load plus QNF. So the same thing is expressed in different ways in our in the notes in the discussed by sir. I guess in that he has splitted this QU as uh, QU skin friction as well as QU, let us say the bearing. So I can write it as QUP plus QUF. But the idea is this skin friction, sorry, this negative skin friction will be at the denominator because it is along with the load. Okay. Suppose if we are given a factor of safety and we are supposed to find this particular load Q, then we can find it as, okay, I'll use the same color so that there is no confusion. We can write it as QU is equal to the capacity that we found out for the pile using this skin as well as the bottom layer. This is the strong layer at the bottom in which it is embedded. So divided by factor of safety uh, minus QF. It is both the equations are nothing but the same, but in some questions we will be asked to find the capacity of the pipe. Another important thing is this is in the top layer, so this is due to the fill. So what are the reasons? So let us say generally cause of this negative string frictions are fill, settlement due to recent fill, which is this case, or it can be soft soil layer. When some soils with which very less very soft, there are some soils which are very soft. It could be at the top or the in between in the stratigraphy, and that can cause higher settlement at the speed of the settlement will be higher than the pile. So in that case that can also contribute. But in such case, so let us say if it is in between, so if this is soft, the problem is more because whatever is in top of this in that layer, that will also contribute for this negative signification, because however stronger the upper layer, it will settle with the soft soil. So we will have to take care of that also. Another thing is sudden drawdown of water. We all know it's a quite famous problem, because when the water table is suddenly draw down, the effective stresses increases because it suddenly becomes the saturated unit weight acting on the different levels. So that will contribute to settlement, and that settlement, if it is faster, it can contribute to negative skin friction of groundwater table. And uh, also it can be like if sudden dissipation of pore water pressure, that is also possible. There is a famous remedy for this. To avoid this, we can stop the contact between the soil layer which is causing this negative skin friction, so that that doesn't contribute. So uh, we can apply bitumen layer. Bitumen layer is quite bitumen or emulsion. There are certain emulsions which can reduce this friction, skin friction. Emulsion layer only for those layers which are contributing to negative skin friction. that, because that's what we want to reduce. So this particular term, so in this particular layer we can give bitumen, so that the it is remedied. uh, so that this particular QNF term is reduced, because our delta will reduce. So if I'm applying bitumen, our delta will reduce and the negative screen friction reduces. So that is the idea. So um, that is one of the remedies, bitumen layer. Okay, layer for soft soil. I should say coating. There's a coating on the pile. Okay, so that is regarding negative infection. This is also applicable for pile groups. The same way that we have done while calculating the capacity of the pile. The only thing is like that particular for that particular layer, it will be negative in the negative direction for that particular layer, as well as if there are layers above it. Okay, so let's jump on to the next question. So in the next question, it's about efficiency of pile group. So in efficiency of pile group, there are different formulas, that directly formulated for only cohesionless soil. So granular soils, it is more easier to predict. So there are this particular formula is famous for that. We can directly arrive at the pile efficiency, pile group efficiency. So let us solve this particular question using that formula. Uh, okay, so we have a 4 into 6 pile, 2.5 meter spacing, diameter of the pile is 600 mm. We have to find the pile group efficiency. So this is the formula that we were talking about, converse Leverrier formula. In that, here we are given n and m. N and m are nothing but the number of rows of piles and number of uh, uh, piles in a row. So let us say in this case we have m is equal to number of rows, that is 4. Okay, that is 4, and our n is equal to number of piles in a particular row, that is 6. That is our 4 into 6, right? Okay, so that is clear. Now other terms are theta is given as tan inverse of d by s. Tan inverse of d, so what is d is nothing but our diameter of the pile. That is nothing but 0.6, so 0.6 meter, and s is spacing, that is 2.5 meter. So this is the center to center spacing, and this is our diameter. Okay, now what is then theta? Theta can be written as tan inverse of 0.6 by 5, 2.5, that is 13.496 degrees. So I can write it directly. Group efficiency is equal to 1 minus, we'll open the bracket, so 4 into 6 minus 1 plus 6 into 4 minus 1 divided by 6 into 4 into our 13.496 divided by 90. Okay, so this turns out to be 0.7626, that is 76.26%. Now if you notice, there is no issue if you are interchanging m and n. So it doesn't matter, because in the equation in the m and n are interchangeable. So 76% we have a option. Okay, that is our problem 3. Okay, Now moving on, this is a certain this problem deals with our finding the capacity. So we have a group, a pile group of 9. We have a 9 pile group, square cross section, rests on clay, unconfined strength is given as 100, length of the pile is 10 meter, cross section is okay. So we have a square pile. Piles are arranged in square pattern and are placed with the center to center distance of 1000 meter. Okay, so spacing is also given. uh, Calculate the safe bearing capacity of the pipe. Okay. Mm, so calculate the safe bearing capacity. We have alpha, NC, and factor of safety given. Both frictional and end bearing we have to consider. Okay. So it's quite straightforward here because we know that the equation is, oh sorry, for the equation is our, for our group we have to take the block. So since it is, okay, so let us first write this. It is 400 cross 400 square piles, and this is our capital B. That will be equal to our 2 times spacing plus one width of the pipe, right? Width or diameter of the pipe. So okay, so spacing is nothing but center to center, and here it is D. Okay, so that's the thing. So I can write it as our group efficiency as CNC plus AC, that is bearing, that is nothing but our B square, capital B square, plus 4 times B, that is our perimeter, that is a shaft, to get the shaft area into length, that is the shaft area, into C, that is our group efficiency, sorry, group capacity for one particular pile. What is it? CUNC into D square. Since it is square, I'm not writing pi D square by 4 because this is square. And our perimeter is 4 4D, right? 4D into L. It's the same way you're writing here. Instead of CU, we should write actually alpha CU, right? Okay, so that's the idea. So here we have this B is equal to 2 into spacing is center to terminal spacing is 1 meter plus diameter is 0.4. So I can write B is 2.4. What else do we need? Another thing here, catch is our QU is directly given as 100 kPa. That is our UCS, that is unconfined compressive strength, which is the result that we get from unconfined compressive strength test. So that is a QU, and so our CU is nothing but QU by 2, that is 100 by 2, that is 50 kPa. So let's jump into it. Our value QUG for the group, that is block failure, we are getting at CU, that is 50 into NC, that is 9, into D, our B square. B square is nothing but 2.4 square plus 4 into B, right? So 2.4 into L. L is the length of the piles. Our length of the pile is 10 meter into 50. That is our CU. This turns out to be 2592 plus 4800 739 kilometer. Let me write it better. 7392 kilometer. Let us see what is our single, when we are taking single pile, our we have 50 CNC, same thing, into zero point 0.4 square. This time it's a square pile, plus 4 into zero point 0.4, that is our perimeter, into length, into adhesion, alpha cu, right? Adhesion into 50. Adhesion is our zero point 0.7 alpha value. So this turns out to be 72 plus 560, that is 632 kilometer. Okay, so we have this thing 632, but that is for one pile. So what is for the uh, total? So our total pile, for total capacity, if I write QU, if I write total, is equal to 9 into 632, that is 5688. So here our group efficiency is higher, but whenever uh, we are trying to design the piles, or so we can say the pile ultimate capacity is 7,000 kilonewton, but the problem is we cannot take it for granted, because here we are dealing with clay. In clay especially, we cannot accept a higher this thing group. We cannot expect the pile to act as a group. The group action may not happen, so we have to only report our lower value. So the lower among the two we can report. We cannot go lower than this value, right? 5,000. So we can give report 5,688 as our QU, kilometer. So what is our safe capacity? QS is equal to 5688 divided by our factor of safety is 2.5. So 2.5, that will be 2275.2 kilometer. So this is our safe capacity of the pile group. So yeah, we have a option also. That is the idea. So here that we need not get confused about whether to report our block failure, whatever we got from block failure, there is a group capacity, or should we give the individual into the number of piles. So whichever is lower we can report, but generally group, when group is lower we have to report the group value, but when we are designing it, we will design it as equal group, this QUG as well as this n into QU is equal to that, like that we'll equate, so that the efficiency is nearly 100%. Okay. uh, so there is a follow-up question with the previous one. For the pile group given the previous question, this is 4. Calculate the corrected settlement using the additional information given. Water table level, water table is at the ground level, and gamma sat is given, CC is given, and E naught, or all the ingredients we are required for consolidation settlement, that is there, and E, that is a modulus of the soil, is given. Poisson's ratio, so for the immediate this influence factor is also there. So the immediate settlement we can find out, and correction factors. So rigidity correction factor is there, and depth correction factor is there, pore pressure. So correction factors are also directly given. Assume the load dispersion rate is 2:1. Okay. So let us start. Here we have uh, okay. So we have a pile group that is the same pile that we were talking about here. So we have, these are square piles, but that doesn't matter, right? So here our idea is we will replace this as a raft. So this is the idea. Here the soil is completely in the clay layer. So we have to assume it as a raft at a level of 2L by 3. So this is the rule that we need to remember. The pile is divided into 2L by 3 and L by 3 when it is completely clay. So here we have clay completely. If it is stratified, we'll discuss it in the coming slides. But when it is, in this case, we have to assume it as a raft at this particular level, and the same procedure that we had done before for shallow foundation, we can adopt here. So uh, just for the argument, let us say, so if it is a raft at this level, so we know that this b is nothing but 2.4 meter. So I can write, if it is a raft of width 2.4, our q, whatever q is equal to 2275 divided by 2.4 square, right? That turns out to be, okay, 2275 divided by 2.4 square. Okay. This is nothing but 394.97 kPa. So we are assuming the raft of which applying 3.497 kPa or at that particular level. So we have that. Okay. So we need not worry about anything else. This is the assumption, basic assumption here. So if you remember this, that is good enough. Then rest everything is carry forward to what we learn in this our shallow foundation. So let us begin our immediate settlement. Let us start our immediate settlement. Okay, my handwriting is not that impressive. Immediate settlement, that is SI. This is the most popular equation based on our elasticity. We all know 1 minus mu square by E into influence factor. Okay, so this is a famous equation. So here Q is the applied load, that is our 394. So let us substitute the values. We have QU as 394.94 into B as 2.4 into 1 minus zero point 0.4 square. What is our mu value? 0.4. In percentage ratio is 0.4. Our modulus is 3 into 10 to the power 4 kPa, and our influence factor is 1.124 square. Okay, so we are treating it as a raft of such a width 2.3 2.4 meter. This turns out to be 29.73 mm. So we have initial immediate settlement. Then what do we have? We need our consolidation settlement. That's why we have this 2:1 thing. This is a 30 degree, that is why it's 2:1. And we know that the influence zone for settlement is 2B. That is our 2B will be 4.8 meter, and we will check the overburden pressure at the middle of the influence zone, the clay layer which is subjected to settlement. So arriving at that, just the good old our good old formula that we use for primary consolidation settlement, that is CC H divided by 1 plus E naught log of sigma dash plus, this is the initial overburden pressure, effective overburden pressure, and this is the increase in effective overburden pressure, and our, so this is our formula. So we can easily substitute. We have the ingredients. I think so. No, we need to find the stresses. So let us find. Can we find it here? Okay, here we can do. So what is the overburden pressure at the level? So we have initial overburden pressure as okay. So what is the water table? Water table is at ground level. So let us say the ground level. water table is at ground level. So our gamma is also given as 20. Is it 20? 20 kilonewton per meter cube. So our effective overburden pressure at a level. So this is if this is 0 meter, and this will be our length of our pile is, length of pile was 10 meter, right? Okay, so this is 2 20 2 into, okay, 2 into 10 by 3, so that is this, and this distance is nothing but 2.4. So I can write our effective overburden pressure is our density, that is our submerged unit weight, that is 20 minus 10 or 9.81, whichever you want to take, into the depth. So what is the depth of this layer? We have 2 into 10 by 3 plus 2.4, right? Am I right? Yeah, like this. Yeah. So that turns out to be 92.39 kPa. And what is the increase due to our pile group? So that is our but we need this particular width. So our increase in effective overburden pressure at this particular depth will be our total load, that is 2275.2 divided by, what is the dimension of this? This is 2.4 plus 2.4 in one side. So that will be on the other side also, it will be square. So 2.4 plus 2.4 square. So I hope you all know why it is 2.4 plus 2.4, because the depth is 2.4, and both the sides it will be half, 2.4 by 2 and 2.4 by 2, and that's how it is. That's why it is 2.4, and adding the height, since it is 2 is to 1. So this value is 98.75. Okay. So we can directly substitute whatever we want. We already have, that is our height of the layer which is subjected to settlement, that is 4.8 meter. I am writing it at mm, so that the answer directly comes out to be in mm. CC is given as 0.15. Our initial void ratio is 0.7. Log of our initial overburden pressure is 39 plus 98. Our increasing is 98 divided by 92.3. So this is 133.72. So we have both the settlements. We can write the total settlement as total settlement is equal to 29.73 plus 133.72. This is 163.45. We are already given three correction factors. 0.8 rigidity because our pile cap is rigid and it can act as a rigid foundation, so rigid raft. And correction depth factor is directly given. If it is not given, we can arrive that at Fox correction chart, which is also there in IS code. And pore pressure correction factor is given as 0.7, which can be arrived at if you know the Skempton's A value, A parameter. Okay, so we are directly, so we can write the corrected settlement directly, that is 163.45 into 0.8 into 0.58 into 0.7. This is 53.08. So this answer is having one of the options. Okay, so we have the corrected settlement. So here just to refresh, This particular correction factor can be arrived from the Fox correction. Just I have the chart. Okay, so I'm refreshing it because till now in the shallow foundation we were talking about this uh, this portion because our it was applicable for that. For pile foundation we will be using this portion. So in order to use this Fox chart, Fox correction curves, we have to adopt that. So what is our L by B? So here our L into B. So L into B is nothing but same. That is our we have square piles, right? So square piles is zero point 0.4 into zero point 0.4. So we have L into B. L and B we can take, and what we have is root of L into B by D. So L into B is zero point 0.4 into zero point 0.4. And D, what is D? Depth of the foundation. Depth of the foundation is our 10 meter. So 10. So we have zero point 0.4 by 10, which is nothing but 0.04. It will come out something like zero point 0.2, zero point 0. So it has to be something like this, but it's in between zero point 0.5 to zero point 0.6. So we can adjust point between zero point 0.5 to zero point 0.6 correction factor, depth correction factor. But in the question they have directly given, so we are not worried about it. But my point is, for pile foundation we'll have to use the second half of the chart, because in shallow foundation we only discussed about the top half. Here we'll use the second half. Okay. And another point that I wanted to convey was this, when we are dealing with different types of layers. So in this particular question we were dealing with the same clay layer was there everywhere. So it was homogeneous. It was homogeneous clay layer, but it might be stratified also, right, in the real life situation. So uh, in the class we had discussed about three different cases. One case was whatever it is discussed now. This is the second case, and this is the third case. In the second case, what happens is we have a stronger layer at the bottom. So the pile is made, it's made sure that the pile is embedded in the stronger layer. So we will not consider the weak soil at all for the settlement, because we are considering we are taking the load transfer completely on the stronger layer. So just as before, we will divide the stronger layer portion, this L1, into 2 by 3 and 1 by 3, just as before. And from the bottom 1 by 3, we will assume the load dispersion is taking place as 2 is to 1. So these all are assumptions. So that is a problem. We cannot practically understand how the load dispersion is at the bottom of the pile after driving it, and how the distribution happens. So these are assumptions, but these are adopted generally when it is in this case. So in this third scenario, what is happening is we have an end bearing pile. So when we say an end bearing pile, the pile is rested on uh, a very strong layer, a very strong firm layer. It's as good as a column. So and it will be actually in reality it will be embedded a little bit, half meter or 1 meter inside this, whether let us say very hard soil or stiff clay. In that case we will take it as a raft at the base of the pile group. So and rest is same, the 30-degree dispersion, that is 2 is to 1, will be there, and we can do the. So in whichever case we are dealing with, we'll assume that there is a raft foundation at that particular level, whichever depending on the case, 2 by 3 L, and or end bearing at the base, and from there we will we'll do just as we had done for shallow foundation. Okay, so that's what I wanted to say. So I would suggest, please go through this IS 2911, first part, first section, annex P, for our or whatever we are discussing. So those formulas are enough, and it will be very useful when we are going into field, and this is specifically for driven pipes. Okay, so yeah, so that's it. If you have any doubts, please do share. You can share it now also. If you are hesitant to speak up, please post it in the here in the comment box. You can put, or uh, you can also post it in discussion forum. Thanks for joining. Uh, Thanks for a good and have a nice day. And the coming session will be on Saturday by Mr. Shivshankar Nandi, 6 to 7. And I will be meeting you on the coming Monday, the next Monday. So thanks again for joining. Have a nice day. Uh, Please post your doubts on discussion forum. Thank you.